remind me every time because I'll probably forget every time. Right, so we're going to be talking about specific types of forces. So we've talked about what force is in general, how there's pushes and pulls and things like that. But up until now, we haven't actually talked about any what any actual forces are. What, for example, examples of them might be, aside from the static friction that I mentioned above. But we're going to go into the specifics here. I can't promise that all of the forces that we're going to talk about in this course are going to be covered today, but a vast majority of them will. So first force that we should probably talk about is gravity. So gravity is actually very complicated. It's not really understood. I mean, it's fairly well understood, but it's not, we don't have good explanation for how it works, and our current best theory does tend to break down. So, you know, there's that. But for the gravity that we're talking about is relatively straightforward. So we might ask the question, why does everything fall at 10 meters per second squared? Without, and that, by the way, that this is on Earth without drag. So in order to understand this, what we're going to do is we're just going to, in order to understand why that's the case, you actually have to get into relatively deep physics. It turns out that the gravitational force is just proportional to mass, and so if the force is proportional to mass, then the acceleration is just the acceleration, because the force from gravity is proportional to m, which basically, this is the magnitude of the force from gravity, which is not surprising, because the force from gravity, we know that if absent any other forces, the force from gravity has to be equal to ma. So the point is that the acceleration due to gravity is just a constant in a given gravitational field. This basically has to do with the fact that inertial mass is the same as gravitational mass. The force that two things pull on each other is related to the mass, to the gravitational mass of those two things, whereas inertial mass is how hard it is to get something moving. It turns out that the m in mg is the same as the m in ma, so you can cancel them, and then you get that the acceleration is just 10 meters per second squared. But that's neither here nor there. I mean, it does answer the question, why does everything fall at 10 meters per second squared? But we can do a little bit better. We can perhaps understand how drag influences this. So first, let's consider two falling things, same size, same shape, everything. But one object is dense, one object is light. So all of their shapes, their shape and their size and all of that, everything else is the same. The only difference is the mass of the two objects. So we know that, like, imagine if you made a feather out of steel and a feather out of a feather. The feather out of steel will accelerate much faster. So we know that the acceleration of the light object should be less than the acceleration of the heavy object due to drag. This is just air resistance. Put another way, we have that the force due to gravity divided by the mass, which is equal to g, that's just what the force due to gravity is, just mg. This is greater than, so, you know, when there's no drag, it's g. This is greater than the heavy acceleration, because even the heaviest thing still experiences air drag. But we can write that out. That's just equal to the force due to gravity from the heavy mass minus the force due to air divided by the mass of the heavy object, which from the above equation, we can just continue this inequality. I'm gonna move this over. Come on. is greater than F light due to gravity minus F air over M light, which is just the acceleration of the light object. By the way I got this was by imagining a free body diagram. If your heavy object has mass m heavy, then you have force due to gravity for the heavy object, and you have the force due to drag from air. And so the acceleration would just be the vector sum divided by the mass from Newton's second law. And the reason why these two forces are the same is because the force due to air resistance is just a function of the shape and size of the object. It doesn't have anything to do with the mass of the object. So what we get then is that the acceleration due to the heavy object is g minus F air over m heavy, and the acceleration of the light object is g minus F air over m light. So what we're getting at is that we're going to show why lighter objects fall more slowly. So why does the heavier object accelerate more? Well, if we compare the accelerations here, well, the only things that are different in these two formulas are the masses. And if you subtract off a term that is smaller, because it's in the denominator and the mass of the heavy object is larger, sorry, it's scrolling all over the place because it's running slowly, this term is smaller than this term. And so the effect of drag, or the effect that drag has on more dense objects, is smaller than the effect of drag on less dense objects. And then, as it should be fairly clear from here then, if there is no air resistance, then the acceleration is just the gravitational acceleration, right? If F air is 0, then then the acceleration is just g. So the formula that we use, which I hope has become fairly clear from here, for gravity it's just the magnitude anyway, of the force due to gravity is just mg. It's just the mass of the object times the gravitational acceleration. And I think you guys have probably all seen something like that before, but if you haven't, now's your first time. It's relatively straightforward as to why that's the case. All right, next force, tension. So tension is a force that's due to ropes or chains and the like. And usually, it's scrolling, I should probably open up a new notepad later. Usually, when talking about tension, we assume that the rope or the chain is massless. And there's a good reason for this, but the bottom line is that if it wasn't massless, then that means that we would have to account for the forces on the rope itself, because the rope would be accelerating and thus would have force. So it just makes things slightly more complicated. So what this does by assuming massless ropes is it allows us to use ropes as conduits for to separate third law force pairs by a distance. So what is tension? Tension is just the force that is applied to a rope, basically. So if I have one end of a rope here and another end of a rope here, and let's say this rope is attached to a block and I'm grabbing this rope. Okay, my arms aren't that long. Let's make this a better drawing. If I pull on this rope with some force, if I pull on the rope with some force, then the rope pulls back on me with a tension. And that's a third law force pair, right? I pull on the rope pulls back. And so when ropes do the pulling, it's called tension. But the important part is that the tension throughout a rope is the same everywhere in the rope. So in particular, me pulling to the left on the rope means that there's a tension on the rope pulling that way. But because the tension is the same all throughout the rope, the magnitude is the tension, there's also a tension from the rope pulling on the block in that direction. And so, again, there's a third law force pair here. So you could imagine then that this block is pulling on me, or on the rope, with an equal and opposite force. Let's just call it force of the block. And so what we found here is that now the force that I have exerted is equal and opposite to the force from the block. Maybe that force is friction, maybe it's somebody else is pulling on that block, whatever. But the point is because the tension is conserved between two, because the tension is the same throughout a rope, the force is transmitted through it. And in that sense, the rope acts as a conduit so that we can have third law force pairs separated by a distance. Normally, third law force pairs are right next to each other because they occur due to contact. But the rope basically allows us to extend our contact. Now, just a quick note, third law force pairs, when separated by a rope, force pairs, has a P and not an F, aren't always opposite anymore. They're not always pointing in opposite directions. In the example above, they were, because the rope was straight. However, imagine that you had again, me pulling on a rope, and we have a pulley that rope is attached to. And then there's a block pulling down. Maybe I'm standing here or something like this. Now, I pull on the rope with some force this way. The rope pulls back with the tension, and then the tension is transmitted through the rope. So now there's a tension pulling up on the block. And the block is pulling down with gravity. So now the equal and opposite forces, assuming everything is stationary, well, actually, that's just true. This is equal and opposite with the gravitational force here. So what we've done is we've effectively, how do I want to phrase this? Yeah, what we've done is we've effectively changed the direction using a pulley. I want to be extra clear here, by the way. The gravitational force isn't actually the third law force pair. It's only equal in magnitude if they are if the block's not moving. Really, the third law force pair is the block pulling down on the rope, right? So the rope pulls up on the block pulls down on the rope. Now, whatever force that block pulls down on the rope with is whatever it is. It might be due to gravity, it might be larger or smaller, but there is that additional force. So just keep that in mind. So just like we'll do with ropes don't stretch, they don't have mass, and so on. We're also going to assume that the pulleys don't have mass, that the pulleys don't, and that the pulleys don't have friction, and so on. Yeah, so for now anyway, we're going to assume that we're going to idealize the pulleys. Right. Next point. There's another type of force that I've already introduced called the contact/normal force. So this type of force is not really a force in the sense of it depends on some outside independent factor. This force just balances other forces. So what I mean by that is that it provides sufficient force to prevent objects from passing through each other. So what do I mean by that? Come on. Yeah, I need to either update OneNote or something because it's acting very slow. What I mean by that is, let's say that you have a block sitting on the ground, right? So there's some gravitational force pulling downwards. But we know that when a block is just sitting on the ground, it's not moving, right? So if that was the only force that was present, if the gravitational force was the only thing present, then we would go and we would apply Newton's laws. We would get that Fg is equal to ma. But we know that the object isn't moving, so a has to be 0. So what gives? Well, the point is that we didn't account for all the forces, right? There's another force, and that's the force of the ground pushing up on the block. We'll call that N, or we'll call that Fc, or we'll call that Fn, whatever, we'll give it various names. And the point is that this normal force, or this force, is what's called the contact or normal force. And it's the thing that exactly cancels out the gravitational or whatever force is pushing the block downwards so that the block doesn't move. So in this case, because A is 0, it's not moving, we have that F net is 0. And what does that mean? It means that the magnitude of this contact force is equal to the magnitude of the gravitational force. Now obviously that's not always true. It's just the gravitational force is the only force involved. However, if it were the case that I was pulling up with slightly less than the force of the ground, let's do another example. I'm pulling up, this is a force of a pulling force that I'm applying. We have gravity pulling down, and then we have the normal force pointing up. I'm gonna draw it here. So again, it's resting on the ground, but my pulling force is not quite enough to lift it. So then what's the magnitude of the normal force? Well, we still know that the acceleration is 0 because it's not being lifted off the ground and it's not falling through the ground, which means that F net is 0, which means that I'm going to put plus y to be in the vertical, in the up direction, which means that F pull plus Fn, let's call it Fc just for consistency, minus Fg equals 0, right? These are all magnitudes. And then now we can solve. So the magnitude of the contact force, or the normal force, is equal to the magnitude of the gravitational force minus the magnitude of the pulling force. And so the point here is that because I'm lifting up on the block with such a force, not enough to lift it, but enough to just like reduce what it would weigh on a scale, the contact force is reduced accordingly. The point being here is that if an object is not accelerating perpendicular to a surface, i.e. if it's not moving up or down, then there will be a normal force to ensure that it doesn't accelerate, assuming that the forces aren't perfectly balanced already. It could be the case, by the way, that I pull up with precisely the right force to cancel out the gravitational force, in which case the normal force would have magnitude 0. But in general, that won't be true. So by the way, a thing to realize about the normal force is that the normal force is what a bathroom scale what a bathroom scale measures, right? It doesn't measure gravity, because you can trick your scale into reading something by taking your scale and pushing it against a wall, and it measures the contact force that it is applying to the wall, or similarly or equivalently, the contact force that the wall is applying to it. All right, so next thing is friction. Fg should be negative. It is, but and then I moved it over to the other side of the equation. So the next thing to talk about is friction, and there are two types. There's static friction, which we've sort of already talked about, but not in a whole lot of detail. And then there's kinetic friction, which we haven't talked about at all yet. But kinetic friction is a little bit easier, so let's talk about that first. So kinetic friction is precisely what people imagine friction to be. It's the force associated with the rubbing of two objects. Oh, come on, come back. And so the direction of the force is it opposes the rubbing or the sliding motion. So imagine that you have two objects sliding one against the other, like if you have an object like this, moving this way on the ground, then the force, the kinetic friction force would be opposing that motion. By the way, kinetic friction doesn't always oppose, that was weird, doesn't always oppose motion, it just opposes the relative sliding of two objects. So sometimes kinetic friction will occur to keep an object in motion. The magnitude of, oh, sorry, you can't see me. The magnitude of kinetic friction is just given by the formula mu sub k, that's the coefficient of kinetic friction, times the normal force. So note two factors, or two things here. First, this mu sub k is a quantitative way of describing how rough the surface is. This is the coefficient of kinetic friction. And if the surface is particularly rough, it will be larger. And if the surface is particularly smooth, like say ice or glass or something, it will be smaller. And this n is the normal force, as described above. It basically describes how hard the two surfaces are pushed together. For example, if you have a very light object, which has a very sliding along the ground, that object will have a small normal force because its gravitational force is small. And so it will slide perhaps more easily than an object that is very heavy. Just because, well, okay, perhaps that's a bad example because the magnitude of the force will go down, but so will the needed force necessary to accelerate it or decelerate it. So, but the point is this normal force basically would increase if you push down on an object, and that makes it harder to slide. One thing to keep in mind about this equation is that this is not a vector equation. This is an equation about magnitudes, because of course it is. The normal force points up from the surface, whereas the frictional force points opposite the direction of the sliding. So you can't have one vector being equal to another vector in a different direction. This is just the description of magnitudes. So static friction is pretty similar, sort of. It's also kind of like the normal force. This is a reactive force, which means that it changes its value depending on the scenarios, and it acts to prevent touching objects from sliding. Acts to prevent touching objects from undergoing or from starting to move relative to one another. So this is the thing that makes it hard to push a car when its brakes are on. Right? The wheels of a car have a lot of static friction with the ground, and the car is very heavy. So the static frictional force is or can be sufficiently large to prevent you from moving the car, no matter how hard you push on it. So just as a reminder, just think back to the inertia discussion we had before. So just as before, or just as the normal force, this is also a force balancer, meaning that the magnitude the magnitude of the force depends on the magnitude opposing it, the magnitude of the force opposing it, and it has a maximum value. So the magnitude of the static frictional force can be at most, meaning it's less than or equal to, some coefficient times n. So this mu sub s is the coefficient of static friction. And again, it basically says how rough is a surface. So imagine like putting a cardboard box on sandpaper. It would be harder to push it than if you put it on ice, because the coefficient of static friction is larger. The point here is that this static friction Fs will equal the attempted pushing force until it reaches its maximum. So after which point the object starts to move. So let's imagine that there's like a rough surface, rough jaggedy surface. Sorry, this is very frustrating for me too. It keeps moving. I don't know why. You have your rough jaggedy surface with your block on it. You have your normal force pushing up on the block. I'm going to be drawing it from the top because it makes it easier. And then I am pushing on it from the right. So this is just some pushing force. Well, because the surface is rough and because friction is involved, we then get a static frictional force opposing that motion. So we have to assume in this case that that the object isn't moving yet. So what happens then is that if let's work out what the if the object is stationary, i.e., even when I'm pushing on it with such a force, F pushing, then what we can conclude is from Newton's second law, we get that the acceleration in the x direction is 0. That's just from observing that it's stationary, which implies that the it must be detecting my hand, which it doesn't usually do, which implies that the force, the net force in the x direction is 0, which implies that F pushing as a magnitude minus Fs is equal to 0. What does that mean? Well, we know then that F pushing is equal to Fs, but Fs is less than or equal to mu sub s times n. So we also have gravity going down, which tells us that we didn't push hard enough. The frictional force was less than the maximum amount. However, if it was the case that F pushing was greater than this amount here, which is just some number times the normal force, which in this case is mg, it's not negative Fs, no. I mean, this is negative because it's pointing in the opposite direction, but this is positive here. Right, if F pushing was greater than mu sub s times n, then the object would be able to overcome the static friction, meaning that it would no longer be stationary and kinetic friction would take over. So what this means is that assuming the larger the coefficient of static friction, that means that it's harder to get an object started moving because the static frictional force will have more potential to oppose whatever force you apply. Eventually, you'll overcome that static frictional force, but it might not but if you don't apply enough force, it won't. Yes, Cody, that's exactly the point. So if you push with a larger force than the static frictional force can apply, then the object starts moving and you're into the coefficient or into the kinetic friction territory. Brianna, that's a perfect question. I was about to get into that. In fact, it's usually the case, and this should agree with your intuition, that the coefficient of static friction is greater than the coefficient of kinetic friction. It's easier to get an object going than it is to, it's easier to keep an object moving than it is to start it moving. And that probably agrees with your intuition, right? If you can get something moving, it's easier to keep it moving than to get something moving from stationary. And that has something to do with the microscopic explanation for how friction works. Like imagine you have two jagged edges locked into each other. Once you break that coefficient of static friction, that basically means that you've almost leveled out the surfaces, and so they'll slide more easily. Jonathan, this is more of a it's not that there's some rule that tells you that this is true. This is just what's experimentally determined. There might be some exotic materials where this is just not the case, but this is a materials property, basically. So, I mean, in most cases, you'll either be asked to calculate one of these or you will be given these quantities. You won't be expected to be able to predict what these values are based off of the material or something. Right, moving right along. The last thing to talk about, the last force, is the elastic force. So the elastic force is a combination of tension and contact, or tension and contact forces, in a way. Think of it like a spring. That's what is the primary example for, not strings. I've been doing too much string theory, sorry. Springs are the primary example of the elastic force. These provide a restoring force. The elastic force is a type of restoring force. And when I say restoring, what that really means is that there is some rest state, or there is some equilibrium state that that spring, or maybe the piece of metal that has a little bit of spring to it, prefers to be in. And that deviation from the equilibrium state implies that there is a force acting to return to the equilibrium. So what I can do is I can give you an example, or I can draw a picture. Let's say that you have a spring, and I'm just going to draw 3 different states of said spring. You have a wall over here. You have a spring that's really compressed. And maybe its equilibrium point is when the block is at this position. And then there's the alternative case where the spring is really stretched. Right? So in this case, the force would be this way, towards the equilibrium. In this case, the force would be this way, again, towards the equilibrium. So in this, that's what I mean when I say restoring force. There is some equilibrium, and that any deviation from it, in this case, a positional deviation, on the left-hand side, there's a deviation, a negative deviation. On the right-hand side, there's a positive deviation, depending on your choice of coordinates. And so those deviations are precisely countered by the restoring force. So Hooke's law is a mathematical description of this statement, which states that the elastic force is equal to K times delta X. So here we have a few different things to introduce. This K here is the spring constant. And it has units of newtons per meter. This delta X here, this is the distance from equilibrium, or this is the perhaps the deviation. It's the reason I'm writing distance instead of displacement vector is because it's in absolute values. And so we can translate this into a vector equation. F elastic is equal to negative K times delta X. So there's a reason why there's a negative sign here, and that's because delta X is the displacement vector from equilibrium to the position, or to the actual position, I suppose. So remember how displacement vectors are defined, right? So in this case, the displacement vector is from here. So you have a vector that starts off with this length. This is, say, x, the vector x equilibrium. And then the actual position vector is here. I'm analyzing this case here. This is the x, we'll just call it just x. Then the so what is the displacement vector? Well, the displacement vector then it's this vector. It's the vector between these 2 points, right? From x equilibrium to x. And so we need this negative sign to flip the direction of the of that displacement vector, so that the force points in the direction opposing the or in order to return to equilibrium rather than being away from equilibrium. So the idea for Hooke's law is basically just that the distance that you are from equilibrium tells you, or is proportional to, the force that the spring applies. Now, this is not, again, this is not always true. A lot of what we're talking about is ideal. But for an idealized spring, this is the case. For a real spring, there's a region of linear behavior, which is what this is called. But, you know, for example, if you take a metal spring and you stretch it out enough, it just stays that way. It doesn't actually go back to where it was. And that's just because this, this linear behavior is only valid in a certain regime. Right. So we're going to change gears a little bit because I know we have a lot. I know we've covered a lot, but we do have a lot to cover today, a lot more even. And I'll try to get through it all. I want to talk about problem solving using Newton's laws. So I'm not going to introduce any new physics. It's just tips and tricks, basically, for how to solve problems. So first, let's talk about pulleys. So pulleys let us change the direction of a tension force for free, right? Basically, a pulley just lets you reroute the direction of some tension force. What it requires is it requires a frictionless pulley and a massless pulley, or sorry, a frictionless pulley / rope and a massless pulley / rope. Massless, frictionless ropes and pulleys are required. So if a problem doesn't say that those things are true, then you probably have to be a little bit more careful. So an example of such a pulley system that might show up in a typical problem is this example of something called the block and tackle. So a block and tackle is a simple machine that basically lets you lift heavy things without using a whole lot of force. So imagine that you have a string attached to the roof of something. Then you have a pulley that's kind of just free hanging. Let me try to draw this better. Here's the setup, the standard setup. So you have two pulleys for a block and tackle. One pulley is directly attached to the roof via some rope or something. Another pulley is free hanging. And attached to this pulley, maybe you have a block with one mass. And attached to this rope, maybe you have a block with another mass. So one question that you might ask is, if neither block is moving, i.e. if they're both stationary, how do the masses of the blocks compare, right? Because I actually really want to redraw this. Sorry, it just looks terrible. There we go. Because this pulley is free hanging, which makes this problem a little bit more complicated, right? You can't just say that they should be equal. So how do we analyze this type of problem? Well, again, we always start with free body diagrams, FBDs. And we have to do a free body diagram for each mass in our object or in our system. The pulleys don't have mass, the rope don't have mass, so they don't need them. So let's do the mass. Actually, perhaps the more appropriate. Yeah, that's fine. So this will take a little bit of work, but we'll get there. So let's imagine that there is some tension T in the rope, right? So we have mass 2. There's a tension force pulling it up. And then there's gravitational force pulling it down. I'm just going to write M2G. Okay, fairly straightforward. What about mass 1, though? Mass 1 is a little bit trickier because there's tension pulling it up, but now we have to go analyze this pulley. We have this tension here pulling up mass 1, gravitational force pulling it down. But these tensions are not the same, right? Maybe we call this tension 2 because they're not the same rope, so there's no reason they have to be the same. Instead, if we want to figure out what that tension is, we have to go look at the pulley really quick, this pulley. So that pulley is going to have the same tension pulling down on it, equal and opposite forces and all that, and tension being conserved. But then look at the rope and how it's attached. What force would you feel if you were to cut these strings here and feel the force on them? Like what would the forces would be equal? They'd both be pulling down, so those forces must be pulling it up. And what would be the magnitude of those forces? Well, it could only be the tension. So what we have is we have two tension forces here that are equal in magnitude to these tensions, because it's part of the same rope. So the takeaway here, and there's more details on this particular problem, is that T2 has to equal 2 times T1. So we can imagine instead that there's two tension forces pulling up on this block. And that's basically just because each of these strings is pulling up on the thing that's holding the block up. So now we can actually do the analysis. We can analyze these two masses. For the mass on the left, we have T, so I'm going to use up is positive. We have T minus M2G equals 0. We're assuming it's stationary. For the mass on the right, I'm going to kill my tablet. We have 2 times T minus M1G equals 0. So if it's the case that these two objects are stationary, which is what we're assuming by assuming that the net forces is 0, this is, you know, F equals A equals MA. And all I'm doing is I'm just saying A is 0 because the objects are stationary, so I'm adding up the forces. We can now solve this system of equations to figure out the relationship between, you guys see what's happening here, how it's so frustrating, to find the relationship between M1 and M2. What we find, by the way, is that they can remain stationary so long as the first mass is twice as massive as the second mass. That's the conclusion here. So pulleys show up all over the place, and you'll see these types of things. But by the way, the point of this whole business is that if you pull down with a force equal to M2, you can hold up an object that's twice as heavy. So imagine that instead of having a mass M2 being pulled down by gravity, you just pull on it with your arms. In this setup, where you have one of the pulleys is free floating, this is called a block and tackle, you can now lift something twice as heavy as you might have been able to before. So another thing that shows up all the time, oh, actually, before I continue, I want to make sure that I talk about, sorry, one moment. There's one other thing I wanted to talk about. And I want to make sure that I get it right. Oh, okay. So the next thing that will show up in these types of problems are things called constraints. And these are just relationships, mathematical relationships, between quantities that describe the system. So for example, one such constraint that will show up all the time, especially if you have any sort of friction, is the constraint on the maximum magnitude of the static frictional force. Right? This is a constraint. This tells you that the static frictional force can be no larger than mu sub s times n. Right? That is something that constrains the value of the static frictional force. So I will give another example demonstrating a constraint, demonstrating how a constraint can show up. So again, let's talk about the block and tackle, this scenario up here. Let's say, so if M2, again, we're not going to assume they're stationary anymore. If M2 drops 10 centimeters, how far up does M1 go? Now this should be a relatively straightforward problem, but there's no but the Newton's laws and all that business has nothing to do with this. This is just a constraint of the system. Hopefully you guys all understand why the answer is 5 centimeters. The way to view this is that if, for example, let's say that M1 goes down or goes up 5 centimeters. Well, it's not like the rope just got shorter. Both of these pieces of rope have to decrease by 5 centimeters. So that extra length gets contributed to the drop in M2. This is 2 times as large because there's 2 ropes going up and only 1 rope going down. And it's not like the rope is stretching or anything. So the conclusion that you take away from this is that in this scenario, the acceleration of the first block is equal to 1/2 the acceleration of the second block. Or explicitly, as vectors, we can actually get rid of these, and just, because we know what direction they're going in as well, we know that the accelerations are not the same direction, one goes up, one goes down. So we can actually say that the acceleration of the first block is equal to negative 1/2 times the acceleration of the second block. That is, if the second block accelerates downwards at, say, 10 meters per second squared, the first block must accelerate upwards at 5 meters per second squared. And the reason is because the rope has to maintain its fixed length. And so this would be a constraint on the motion of the blocks. And so while you may be able to lift something twice as tall, you can only lift it half as far. Another example. Oh, unfortunately, we're not going to get as far as I would have liked today. Oh, well, we'll have to put it off. Another example of something that will show up in problems like this is the inclined plane. So the inclined plane is a standard problem that you'll see in this type of course. Maybe all it is a slope or a ramp. So in this case, maybe you have some angle theta here. This is a right angle almost always. And maybe you have a mass up here attached to a rope, attached to a pulley. And then that pulley is attached to another mass. For example, maybe one's capital M and one's lowercase m. So you might ask the question, oh, and maybe there's some coefficient of friction, of static friction, mu sub s. The question might be something like, if neither block moves, what is the minimum value of m? So the situation to imagine here is something like, clearly, if let's say lowercase m is like 10 kilograms. Clearly, if capital M was 100,000 kilograms, capital M is just going to slide down and pull little m up, right? Alternatively, if little m is 10,000 kilograms and capital M is 10 kilograms, well, little m is going to win. It's going to pull capital M up. But there is some sweet spot where, because if there were no friction, if the two force, there would be some sweet spot where basically the masses would be related to each other such that they would perfectly balance. And if there's friction, sorry, I'll make little m littler. There, hopefully now it's more obvious. So there is some sweet spot because friction can kind of account for that excess force, right? If, say, little m is 100 kilograms and capital M is 101 kilograms, it could be the case that for a sufficiently small angle, or for a sufficiently large angle theta, anyway, it could be the case that the friction just barely, or the friction can overcome the desire for capital M to pull little m up, right? There's this excess force. And similarly, if capital M was slightly too small, then the friction force might prevent the capital M from sliding and moving up rather than down the ramp. So how would we solve this problem? Well, it is 1:59, so unfortunately, I guess that means that I should probably put this off until next time, which is not nearly as far as I would have hoped to have gotten. But I will leave you with the, in suspense, how you solve this problem to find the minimum value of m. In fact, if you're curious, you can go check either the textbook or work it out for yourself, but I'll go over it again at the beginning of lecture next week. But it's not that hard of a problem, but it does require some work, so maybe think about it a little bit. I'm going to let you know that probably, depending, like, I'll try to prevent this from happening, but probably come Friday, I won't have finished everything I needed to for the end of the week, so I might have to go over on Friday. If you can't make it, like if you have to leave immediately, do remember that the lectures are recorded, and so if you do miss the last 15 or 20 minutes, then you can go back and watch them. Yeah, this is quite literally a cliffhanger. it actually turns out that the answer is nice, but it's a little bit involved. So I don't want to, you know, spend 30 seconds going over it and then have you be confused. Right. So I'm going to stop recording here. And I will